Okay, this one's properties of definite integrals and the mean value theorem. So I've rewound a lesson on you now. You're good? You're with me? If your brain's had enough, you're just locked right up, don't worry. This one is not bad. This really just talks about some properties that are probably close to self-evident already. Or at least when I show them, you'll go, oh, well, that makes sense. Just useful little things about the definite integral. Let's talk about integral a to b f of x versus integral from b to a f of x. If they ask you for an integral going the other way, every single x interval will be flipped. And we talked about doing x2 minus x1. Now it'll always be the left minus the right. And so you get negatives all the way along here. That's the end of the story. We're going the opposite direction with this. The interval from b to a, every single delta x will be the other sign. That is, these little delta x's will all be negatives. Which doesn't make any sense. Why would we do it that way? Like if I went up here on the board here and said, I've got an interval that goes from 11/5 to 12/5, and I said, how wide is it? You'd take 12/5 and subtract 11/5. What this is saying is if you go the other way, b to a, and you go 11/5 minus 12/5, this will give you a negative value. What does that mean? It just means that the integral from a to b and the integral from b to a will have the exact same values, except one will be negative and one will be positive. That's all. You just have to watch out if you go the other way. So a cute little property, I'll use it in an example today so you can see how this is used. If you want to go the opposite way for some reason, you want to do the integral the other way, that's fine. You just have to change the sign of the whole thing. Here's a bunch of rules for definite integrals. There's a very analogous derivative page like this, where you find out, after days of doing the derivative, you find out that what you're doing is okay. Like the integral we just did earlier. There was just several pieces added and subtracted together. These properties say you can find the antiderivatives of the individual pieces. You can find derivatives of the individual pieces and add them up. So let's just go through these. If you want to reverse the direction of integration, and you want to go a to b instead of b to a, you just have to reverse the sign. If you go integral a to a of f of x dx, you get 0. Let's just put some numbers in there. If you find the antiderivative between 5 and 5, that is, you want to find the area of a curve between 5 and 5, there's going to be nothing under that curve from 5 to 5. So its area would be 0. Constant multiple. We've done that in some of the even sums. You can common factor out of an integral, no problem. Sum and difference, if you've got several things added together in an integral, you can break it into adding separate integrals and vice versa. If you've got two integrals added together, you can put them together. Oh, this one's different. If you want to find the area from a to b and add to that the area from b to c, you'll get the area from a to c. You don't need to break those up. If you go, oh, find the integral from 0 to 5, add that to 5 to 10, you could just do 0 to 10. Or you could break them up if you want. These are just handy properties that you can use. I'm going to use all these in some examples in a minute. These ones are a little harder. If max of f and min of f are the maximum and minimum values of f on a to b, then the integral will be bigger than the minimum rectangle, and it'll be smaller than the maximum rectangle. And I've used rectangle as a word on purpose to say you'll be trapped between your minimum and maximum values. Maybe that needs a little picture. Yeah, that's the examples next. So I need a little picture of the min-max thing. And I'll draw a really simple function to start with to get this min-max thing under control. And my simple function is going to be increasing right like that. And if I want to find the area under this curve from some a to b, well, let's talk about three different areas. We'll talk about the area using the minimum value, and I'll try and draw that with a filled in yellow rectangle here. Let's see how it goes here. There's one area, that's not a rectangle, rectangle, there we go. See, there's one area that finds the area using the min value. That'll be smaller than the actual answer. Do you agree that the actual area will be bigger than that? Okay? Then if I draw a rectangle up here, and I don't know how I'm going to exactly do that, without blowing away everything, so we'll just throw that out of the way. If I draw a rectangle using the max value, can you see that big rectangle there? You agree that's too big an area. Once you see the picture, you're like, well, that's not very interesting. You're saying the actual integral's bigger than the min and less than the max. Yeah, actually, that's all that one's saying. You know, not too complicated there. Once you see pictures of it. Back to here. Here's what we want, some examples. After seeing all that, it's like, oh, I'm a little confused. Let me use them in action, because they're actually very nice when you use them in action. I've got them on a separate page here. Okay, suppose you have this information, and if it seems weird, just made up information. Actually, this is the type of reasoning that'll happen with integrals sometimes. What we know is the integral from -1 to 1 of f of x dx is 5. The area under some curve from -1 to 1 is 5. That's all we know about the function. Oh, sorry, we know something else. The integral from 1 to 4 of f of x dx is -2. So apparently it ducks under the y-axis there for a while. Now a different function, h, we have some information. -1 to 1, the area under that curve is 7. So the big question they want to know is, what's the integral from 4 to 1? Just give that a stare for a second. They want to know the integral from 4 to 1, and the only information they've given us is the integral from -1 to 1, the integral from 1 to 4, and something about h to x, which isn't going to be useful here at all. How can these two pieces of information about f help us to find the integral from 4 to 1? That is, which one of those is actually sort of helpful? What do you notice about this 4 and 1? Where else do you see the 4 and 1, Brad? This one was 1 to 4. So it said, when I found the area from 1 to 4, I got -2. When you do from 4 to 1, you'll get the negative of that. You can flip the limits of summation, but then you get negative delta x's all the way along the way, and you get a negative answer. And so I've got the negative there. And maybe I've shown too many steps here and overcomplicated it here. Because basically all we're saying is the derivative one way from 4 to 1 will be the opposite sign of the derivative the other way, which is 1 to 4, so I get positive 2. Let's try B and see if B helps you to see where these things are getting at here. It says find the integral from -1 to all the way to 4 of f of x dx. The only information we have is from -1 to 1 and from 1 to 4. What can I do with those two areas to get my full area from -1 all the way to 4? Add them together. This one says go from -1 to 1. This one says go from 1 to 4. So I've just got to go 5 plus -2. And the subtracting areas is weird. And basically what we're saying is net area. The positive area, subtract the negative area. Sorry, I'm going to break some technology here. Okay, any ideas here? What a mess. They want interval -1 to 1 of 2f of x plus 3h of x. How can I possibly deal with all of that? Brad, what do you like here? he says first, break this into two integrals. We're totally allowed to do that when we're doing integrals, is to say, well, instead of going negative 1 to 1 of all this stuff added together, I'll do negative 1 to 1 of 2f at x plus negative 1 to 1 of 3h at x. Then he said more. He kept right on going. He saw what was going to happen next. And maybe once you see it, you'll be like, oh, I see what you did there. That's not the information we have. We've got negative 1 to 1 of f at x, not of 2f at x. But he said, oh, just common factor. I don't know if he used the word common factor. You just bring the 2 out. Say this is 2 integral negative 1 to 1 of f at x dx. And this is 3 negative 1 to 1 h at x dx. And those are the exact information they gave us in the question. F at x, negative 1 to 1 of f at x is 5. And negative 1 to 1 of h at x is 7. And I get a value of 31 there. Then they want 0 to 1. And I want to reread the question for you to prepare you for this type of question. For each of the following integrals, find each of the following integrals if possible. 0 to 1, there's no way to break this up into 0 to 1. We might want it to be half of this one. Negative 1 to 1, half should be 0 to 1. But we don't know what the function looks like. We don't know if it goes up and down and around. If we knew it was even, or maybe odd, if we knew a little bit more about it, we might have a chance at some symmetry here, and those things might come up in later sections and later, but we don't have that information here. So we can't do that with what we have here. There's no way to break this down. There's no way to automatically know it would be half of that. E, negative 2 to 2 of h at x dx, same thing. They gave us negative 1 to 1. We'd sure like it to be double. We go, okay, well then we can do double from negative 2 to 2, but we don't know what the function does. They didn't give us any information. So we can't do this one either. Sometimes it's just as hard to decide you can't do something than to find a way to do it. So these are challenging because you have to be able to look at them and know what you can and can't do. Last one, negative 1 to 4 of f at x plus h at x. Can anyone tell me why this one can't be done? We don't have enough information about h at x to do, so we can't do it, because we don't have enough information there. We have enough information about f. We could do f, negative 1 to 4, no problem, but h at x, we don't have enough information to do it there, and no way to extend that, no way to just multiply, not without more information about h at x. Starting to get skeptical here. Okay. Show the value of 0 to 1, square root of 1 plus cos x is less than 3 halves. I don't even know what square root of 1 plus cos x looks like. I certainly don't know how to take the antiderivative of that mess. You know, like, we're just barely working on x squared and x cubed. We're just sort of getting warmed up on something with an exponent on it, let alone something with a square root with a 1 plus cos x under it. But this phrase sort of tips my brain to something. It's like, it's less than 3 halves. They didn't actually ask me for the value. They asked me for less than a certain value. And I don't know about the square root of the 1 plus or anything like that, but cos x. Let's talk about cos x. Cos x has some very specific rules to it. And the most it goes to is 1, and the lowest it goes to is negative 1. So the most cos x has max value of 1. That's the most cos x can get to. Therefore, square root 1 plus cos x has max value of root 1 plus 1 equal to root 2. That's the most that square root 1 plus cos x can get to. I don't know what the function looks like. I never do find out in this question. But I do know that if I draw a rectangle that goes from 0 to 1, that's what they wanted, integral 0 to 1, and I draw a rectangle that has height root 2, here comes my rectangle, that this function never gets above that. It never goes bigger than that. I don't know where it goes. It could go up and down and around, but it's always going to be smaller than this rectangle because it never gets above root 2. So the max value, integral 0 to 1 of root 1 plus cos x dx is less than or equal to 1 times root 2. It could be as big as all that. It's not going to be, but it could be as big as all that, which is 1.4. Right? If you do the square root of 2, it's 1.4, which is certainly less than, strictly less than 3/2. An application of that max part of it. I'm going to do the second half of that. That was properties of definite integrals and the mean value theorem. The second half will be a separate video, mean value theorem.